Okay, we talked about innate immunity, now we're talking about adaptive. In the last video we talked about the beginning of adaptive, like terminology use. Is it passive? Is it active? We talked about HLAs and MHCs, what they are. We talked about antigen presenting cells. Now we're going to talk about the lymphocytes. So lymphocytes are really important key player cells in the adaptive immune system. Right. So again, here's a little chart. You want to make sure that you understand these different cells. When you're looking at the cells, you have to ask yourself, what's that cell there for? If you understand what the cell's there for, and then suddenly you lose the ability to make that cell, you can predict the outcome of the disease. So if I tell you something like the T cells, just like a foreshadowing, T cells, they're there to kill virus-infected cells and fungus cells. If you lose the ability to make T cells, what types of infections are you going to get more commonly than the average person? You're going to get virus-related problems, like the common cold repeatedly, herpes outbreaks repetitively, more commonly. You'll get fungus infections, like real bad toenail infections, maybe fungus in your mouth. Those are signs that you might have a T cell problem. If the T cells are there to fight off viruses and fungus, and then suddenly you're getting lots of virus and fungus disorders, you might want to worry about, is your T cell keeping up to speed? All right. So cellular responses, when we talk about these, we're going to subdivide these again. We're going to go between the humoral and the cell-mediated adaptive immunity. So humoral, this is named after what Hippocrates said way back hundreds of years ago. He believed that there were basic humors or basic fluids in the bodies. So what we're saying is humoral immunity is there's something that's floating in the blood fluid of the body. I mean, current immune scientists back in like the 50s and 60s, they didn't understand this either. They knew that something was happening in the fluid of the blood. They put the blood fluid with no cells on top of a bacteria, and then suddenly the bacteria would die. So they knew it was something in the humors. The other type is cell-mediated. Cell-mediated means that the cells have to be there. So same kind of scientists, they're putting cells like blood cells and white blood cells in the blood sample and then dropping bacteria in it, and they're watching the cells actually attack the bacteria. Then they know it's cell-mediated. It's a cell doing it. So humoral means something's floating in the fluid that's basically too small to see. And the other one is cell-mediated, where it's the cells themselves in the fluid that are trying to chase down and attack things. So cellular and humoral responses are not independent. They work together, hand in hand. They need to both be working. Diseases like HIV will actually attack one part of that, and both sides fail. Right? So humoral immunity is fluid immunity, and it's the antibodies we're going to poke fingers at. Right? Cell-mediated means that the cells have to be either in the T cells or the T cells that have to be there. Right? So these cells of the immune response are different from the inflammatory response because the adaptive immune response are specific. They have to know exactly what they're looking for. They have a lasting memory. So they see it once and they remember or get better at doing it later. Okay? And so what we call this immunity. We call it lasting immunity. When we get vaccinated, we're getting vaccinated for this lasting, long immunity to something. Right? And then remember, it's the antigens that trigger that immune response. So let's start with the humoral immunity. Humoral immunity, these things you definitely want to remember. It revolves around the B lymphocytes. Humoral revolves around B lymphocytes. So B lymphocytes, excuse me, they're made in the bone marrow, they mature in the bone marrow. They can make potentially up to 1 trillion, actually. So even more than this, they can make up to 1 trillion different antigens. But only one B cell can carry or be able to detect one antigen. So if this B cell detects round shapes and a square dangerous shape bumps into it, it doesn't do anything about it. It just lets that dangerous square shape fly on by. Sensitive to only one B cell sensitive to one antigen, right? So they detect an antigen. When they detect the antigen, then they kind of put on their super cape and they become a plasma cell. So they differentiate into a plasma cell, and this plasma cell starts cranking out antibodies and throwing it left and right and all over the place. They're throwing out these antibodies, and these little antibodies here, those attack the bacteria and try and either isolate the bacteria or kill the bacteria. The other thing they can do is they differentiate into a memory cell, and the memory cell is not there to fight. The memory cell runs off. It hides in a closet until the infection's over, and then it comes out of the closet. The next time you see that infective agent, it's ready. It remembers it. It goes, oh, I remember back in 1983 when you had this thing happen to you. We know what this is like. We're going to attack it and kill it. Right? The B cells produce things that are called antibodies or immunoglobulins. And antibodies and immunoglobulins are usually used interchangeably. But technically, the antibodies are when they're free floating through the blood, and immunoglobulins are when they're actually stuck to the surface of a cell. So there's a little bit of a difference. They're both the same thing, but one's free floating out in the blood, and one's actually stuck onto a cell. Right? So when they're free floating in the blood, we call them serum glycoproteins. Excuse me. So they're just sugar proteins floating around out there. All right. So here's another example of the pathway. You have this B cell that's activated because it's exposed to an antigen. It starts proliferating or replicating, and it just keeps dividing over and over and over again. Half of these are going to turn into plasma cells, and you can see the plasma cells rough endoplasmic reticulum gets really thick because it's making lots of what? Proteins. These antibodies are proteins. So they crank this up, they're cranking out lots of antibodies, and when they're done, they die. The memory cells are going to hide off in the corner so that later when the infection comes back, they're ready and they can attack and you get a faster response. So next question here is define antibody, describing the molecular structure and function of the antibody. I'm not talking about describe the blue components and the red components and the yellow. That's not what I mean. So first of all, you want to know that an antibody and an immunoglobulin are basically the same thing. So remember, antibodies are free floating. Next, you want to know that they work like a lock and key. So this is that Y-shaped antibody. Up here at the surface, you can see this little code. All these little grooves are like the key for your house, but where your house only has 5 to 6 grooves, this thing will have lots and lots of grooves. It's very specific to one antigen. Right? And then you want to remember what cells make it. What are the types of cells that make antibodies? They're B cells. And when they're producing them in rapid amount or high amounts, they're called a plasma cell. So if they're an activated B cell, it's called a plasma cell. And then the last thing here is the antibodies have different actions, or we call them classes. So there's more than one type of antibody. When you look at the structure, you can see it looks kind of like a Y shape. And we'll describe what it means to be the FAB and FC part. Here's a cell, and you can see the antibodies surrounding the cell. Right. So what's it meant by the antibodies' direct or indirect effects? So direct effects, if an antibody is out in your circulation, it can actually directly make contact with the bacteria. And you see this antibody's key or lock section fits perfectly on the antigen. So it binds the antigen and holds on to it. So if this antigen, if these little red triangles are dangerous and they could kill you, if that antibody binds to that area and keeps it so that it can't kill you, it's called neutralizing it. It neutralizes the bacteria or the toxin. If you have little tetanus toxins floating out here that can be harmful to your body and you have an antibody against it, it binds the little tetanus toxin so it's not dangerous for you anymore. So neutralizing things like neutralizing the powerful or dangerous parts. You can neutralize a virus the same way. If an antibody sticks to a virus, it can't get into the cell to replicate. Another one, agglutination. So you can see this group of antibodies are stuck together. They're holding this bacteria, that bacteria, back that bacteria. So they're sticking together. I always think glutinate, like sticky, gluten. Right? Another funny thing about this is agglutination. I always think of that mother that's walking through the store with 3 kids. So the kids are running all over the place. What's she do? She finds some way to attach the 3, and they move slower. This is perfect because if these bacteria are moving really slow, they can't replicate, they can't hurt you, and they can be removed from the system a lot faster. So this agglutination causes kind of a clumping or sticking effect. And this last one, precipitation, is a settling effect. So if I have this one bacteria here and all the antibodies stick to it, it's almost like weights dragging it down out of the circulation so that it can't be dangerous. Those are 3 direct attacks. Direct attack isn't very powerful. So an antibody directly attacking these, it holds them in place, but a lot of times it doesn't actually do the killing. So that stuff can just sit there for a while. Indirect signal would be opsonization. And opsonization, like I said before, is kind of like buttering the bacteria so that other cells love it. So in this situation, the antibody sticks, Well, when the antibody sticks, it also releases chemotactic factors, or a chemotactic property, that attracts white blood cells and says, hey, look at me, look what I caught, eat us both. And the white blood cell will eat the antibody and it eats the bacteria at the same time. So opsin makes it so that it can signal others and hold this in place so it, well, basically can be eaten up. And you can see some of the examples down here too. Alright, so I had a little short list down in the corner. You can see what's going on with direct attachment versus activating other things. Like when it activates complement, then complement comes in and additionally opsonizes. You can see an antibody has lots of different effects all through here. So it activates lymphocytes, it works as an opsin, so it sticks all over the surface of it. It can actually trigger phagocytosis. So this is like putting butter on the surface of the bacteria, and now that phagocyte definitely wants to eat it. Right? It can activate other cells, like mast cells. It can, well, I said that, but it's up here. And then it can actually activate complement. So there are a lot of things antibodies can do. Tons of things. But the most powerful thing that they do is actually indirect. Indirect amplifies the signal. It makes it bigger. It triggers complement. It triggers other things to come in and start eating. Right? So direct works, it's just not nearly as powerful as indirect. Here are the 5 classes, or we also call them isotopes, and you have to know these. I always remember the word gamed, G-A-M-E-D. So when I'm looking, the G's are the first ones. So G's are the most abundant in your system. Where am I? There we go. So G's are all over. About 80 to 85% of the circulating antibodies are these G's. G's, the special things you want to remember, is one thing they do is they fix complement. So they help secure complement. They help activate complement. Right? The second thing you really want to remember is that G can cross the placenta. So G can actually get across the placenta. If you have, well, it's going in to protect the baby. Unfortunately, it's also G that goes across and can attack a baby's blood. And we'll talk about that later. Erythroblastosis fetalis. The next one of the word gained is A. So IgAs, or immunoglobulin A, you can see it's like 2 antibodies stuck together. So kind of powerful. IgA is super important because it's in all the secretions of your body. So it's in the blood, or it can be in mucus. It can be saliva. It can be in milk from mom. Mother's milk is full of IgAs. It can be in tears. It basically lines the surface of your body, so it goes all over the surface of the body and helps protect you from invaders. When a mom breastfeeds her baby, that's what's happening, is that these IgAs are going from mom and they're dripping into baby's mucosa. They're going through the baby's mucus, down through baby's GI tract. But remember, the mucus can also pull things into the respiratory tract. So it's protecting baby. That's what the IgA does. It's protecting you too. If a bacteria gets on the surface of your body, the IgA will stick to it and help you to get rid of it. All right, the next letter is M, and M are like these big Chinese throwing stars of death. Look at all these antibodies poking around. They're big and huge, but in reality they actually don't do as much damage as the G. But they're called a pentamer. There are 5 of them stuck around here. It's the biggest of the immunoglobulins. Right? And the key with this, when we talk about response, this is the key antibody or immunoglobulin made during what we refer to as the primary response. So when you're vaccinated as a kid to chickenpox, right away your body's going to make tons of these IgMs. But 3 years down the road, when you're exposed to another kid with chickenpox, it's actually the IgGs that are kicking in there. So I'll show you what that means. Next ones are the E's. E's are super important because E's are associated with histamine and allergies. So IgE is ideally the least concentrated. There aren't that many there. But it sensitizes things like mast cells, basophils. It makes them so they're more reactive, and that's what an IgE does. Right? IgA is also really important for doing things like attacking parasites. So those are some keys you want to remember. IgD up here is actually kind of a mystery. We know it's on the surface of the B lymphocytes, but other than that, we really don't know why it's there. So those are your G, A, M, E, and D. G is the most abundant. I gave you some features. I gave you features of A. I told you where to find them. So you really need to know those. Right? So just as a refresher of a couple of the important ones, IgEs, I told you already, IgEs, they're for parasites. and allergic reactions. So when IgE sticks to the surface of a mast cell, it just sticks there. It's waiting. So now this mast cell is covered by these antibodies. If that invader comes along and triggers the antibody, it's like flipping a switch to degranulate, and then you release histamine. Okay? Remember, you also release the eosinophil chemotractic factor, which is going to pull in eosinophils to start eating up parasites. That's what IgE does. Right? And I kind of answer these questions, but which granulocyte focuses on parasite attack? It's the eosinophil. Right? And then you already know what's in the granules. So full of histamine, heparin. Did I skip a slide? No, I didn't. Right. And next, IgA. IgA is in all the mucous membranes. It's in your mouth, it's in your throat, it's in your GI tract, it's in your reproductive tract. Mom gives it to baby to help protect the baby. Right. And then that primary and secondary response. So when you get vaccinated, they call it the primary response. It's the first time you're exposed to this thing. When you're first vaccinated, your IgMs will go up, but look how slow they go up. So you're exposed to this thing, and for about the first 10 days, you have this really slow response. This bacteria is replicating like crazy. And you're going, you're waiting and waiting, and then finally, look, your primary response comes to its peak at about 21 days in. Almost 3 weeks is when you're completely over that, actually. You've made enough antibodies that you've killed off this bacteria and it's not there, and you're kind of safe. That's the primary response. IgM is the primary antibody produced. Now the second time you're exposed to it, they call it the secondary response. But look at this. You're exposed to it, and within just a few days, you're already at the peak of the first response. So within 3 to 5 days, you're already at a peak, but you're still rising. You're making more and more antibodies. You're cranking these things out. They're flying everywhere. The second response is primarily because of IgGs, though. A lot of them were already circulating in the system. Now you're cranking out a lot of them, brand new ones. They're simple. They're easy to make. They're not like that big pentamer, the M pentamer. So the first response can take 10 or more days for you to respond. That's why you get so sick and you get cold and you feel like crap. Right? But the secondary response can happen within days. Quick response, in fact, you could be exposed to something like chickenpox. It's in your system. You get a little running cold. You may get a little bit of a low-grade fever, and then you're over it. That's all it did. Somebody in their first response, they can't respond fast enough, so all those little hives start breaking out. All right, so first versus secondary, or primary versus secondary response. Next, discuss some of the alterations in immunity for infants and the elderly. And right now I'm going to talk a little bit about infants, and at the end of this video, this set of videos, I'm going to talk about the elderly. So first, when you're born, basically you're this little sterile creature. You haven't had to have an immune system. Mom's protected you. Any of the immune functions you have inside of you were given to you by mom. You haven't had to make squat yet. So first of all, what kind of immunity is that? Is that active or passive? You haven't made anything. Mom gave you everything. It's passive, right? Well, if you look at this chart here, this is during gestation. 3, 6, 9 months. Look at all those immunoglobulins that are in the baby's blood right now. Tons of IgGs in there. But she's still in mom, right? And then at 9 months, she's born, and now that she's left, look at her immunoglobulins. They're plummeting because these were given from mom. They're not attached anymore, so they're plummeting really, really, really low. And it takes around 6 to 8 months before her natural immune system will start kicking in to make up for it. But look at this. Around 6 months, her immune system's really low. And she starts building it up, building it up, building it up. So it's a lot bigger around 12 months of age. But again, when you're first born, your first response to things is going to be primarily IgMs. They're not nearly as effective as IgG. And a baby's not able to make IgGs right away. They don't know how to make it. They haven't learned to make it. They haven't been exposed to things to know how to make it. So that's why a mom should breastfeed, is because when she breastfeeds, she gives the IgAs primarily through breast milk. While the baby's in the placenta, here's the placental barrier. The only Ig that can go across is the IgG. So mom's just basically loaning the stuff to baby, and then the baby gets rid of it and starts developing its own. So, homework question number 8. So you're going to look up what is hemolytic disease of the newborn. So you're going to look that up and tell me what it is. And you probably already know it. You may have seen different names for it. But so what is it? Hemolytic disease of the newborn. How many babies are affected a year by this? And then what are 2 types of incompatibility that cause it? So just tell me the 2 types of incompatibilities that cause hemolytic disease in newborn. And then what isotype antibody causes it, and how do you know? So what's the type of antibody that can actually cause the baby's blood to be attacked? And how do you know? If you want to say lecture, just tell me the slide that you saw before. All right. And oh, there we go. So pediatrics. So we already talked a little bit about neonates. They have this depressed immune system. They're very susceptible to lots of different things. Right? Their neutrophils are dumb. They don't know how to work yet. They've never had to use neutrophils. So they have neutrophils, but they don't know how to turn their sniffers on. So they're bad at chemotaxis. They just wander around bumping into things, not knowing how to aim, themselves. Newborns have less complement. That complement cascade's not working yet. So look at all these systems that are shutting down. They're not working appropriately. They can't make reactive oxygen species, so they don't make those free radicals to attack bacteria. And then, as a result, they have a tendency to get overwhelming sepsis. Because when a bacteria gets in, they have very few defenses to actually kill it. So if that bacteria is allowed to replicate, then it can cause big problems for that little kid. Right? And then the last part, cell-mediated immunity. So humoral immunity revolved around antibodies in the B cells. Cell-mediated revolves around T cells. T cells like to get their hands dirty. They get in, they grab hold of the invader, and they punch holes in the invader. B cells don't like to do that. B cells throw antibodies out in the environment. They circulate through the blood and try and kill the invader. Right? So first, T cell maturation, you already know this. Where's a T cell made? It's made in the bone marrow, but where's it mature? The T is telling you thymus. Yep. So here I have the mediastinum. The thymus is right here in front of the heart. And the thymus, as we age, after the age of 25, our thymus actually starts shrinking. So it peaks in our teen years or early 20s, but after our mid-20s, it starts shrinking and shrinking and shrinking. And they believe it's because you should have already reproduced at that point, and it's too much energy to keep up that thymus, so let's just get rid of it. So unfortunately, without a thymus, what cells aren't going to mature appropriately? Right, the T cells. So you can see the pieces coming together. Right. So T cells come in 2 flavors, or 2 general flavors. You can actually break them down more, but they come in the CD4 and the CD8 cells. So when you're looking at these are also known as the T helper cells, and these are known as the T cytotoxic cells, or cytotoxic T cells. Right. So as they're made in the bone, they move up into the thymus. They already know if they're going to be a CD4 or CD8, but then they mature. They learn. If they're focused on attacking self, they're killed. But once they're moved from the outside part of the thymus to the medulla, they become immunocompetent. They're able to work now. Right? Then they're released into the blood. They can move over to the lymph nodes. They can circulate in the blood. They can go wherever they want at that point. Right? And then various types of T cells. So lots of types. The main one you're going to hear about is cytotoxic T cells. Well, one of the 2 main ones. We also call them CD8 cells because they have a little receptor on their surface, and it's called CD8. Cytotoxic cells, they get their hands dirty. I used to use a lot of analogies to the military with the immune system, but if I had to say this cell-mediated, it's like the Marines. They like to get their hands dirty. They like to get in. They like get physical. They punch holes in the invader, and that's how they kill the invader. That's what a cytotoxic T cell does. It has granules, and it gets up close to the invader and just starts spitting the granules on it. Right? Those granules are called perforins because they perforate the membrane. So cytolytic cell lysing enzymes, perforins. Right? Or they have direct receptor interactions. So if it's a human cell, if it's your cell, but it has a virus in it, the cytotoxic T cell comes up to it and says, I know you're one of us, so I'm not going to kill you. You're going to kill yourself. and it flips a receptor on so that apoptosis happens. Okay. Next, you have the delayed hypersensitivity cells. So we'll talk about these more in the next video, but these are T cells. They usually take about 24 hours to work. So they get this response, but they drag it out, slow to respond. And we'll talk about this primarily in poison ivy. And then T regulatory cells, or T reg cells, these things are like the military police. So if these are the drunken Marines, these are the military police that keep them in line. Because these things, they want to destroy. Their job is to punch things. So if they have nothing better to do, they'll actually start attacking your own cells. The T regulatory cells say, this is self. Don't hurt it. Keep it intact. Right? So the T regulatory cells, or sometimes you'll hear them called T suppressor cells, they turn down all the other cells. These cells don't get out of hand. And then the last one's the T helper cells. These are another one just as important as the cytotoxic T cells. The T helper cells are kind of like the president of the immune system. They're the commander-in-chief. They govern all the other immune cells. T helper cells tell the cytotoxic Ts what to do. They tell other cells like B cells what to do. So they're kind of the commander-in-chief of all the military branches. And we call them CD4 cells because they have a CD4 receptor on the surface. Here you can see the hematopoietic cells again breaking down, and then you can see the bone marrow. You make the B and T cells here, but the T cells escape, go to the thymus mature, and then they go hang out in the lymph node, waiting to kill something. All right. So APC, we talked about antigen presenting cells before. Here's an example of how it works. So you have an antigen presenting cell here that presents itself to the T cell. It says, hey, there's a copy of the antigen. That antigen is the invader. The T cell says, great, got it. We're going to do our job now. So now that T cell, it's going to differentiate. It becomes an attack cell, but it also becomes a memory cell that hides in the closet with that B memory cell for later invasions, so that you're more prepared later when it comes back. Okay. So cell-mediated immunity, I already talked about this through the TC cells primarily, cytotoxics. T cells don't produce antibodies. Only B cells do. So the T cell's weapon is they find the invader, they match it up and say, oh, yep, there's a problem with this cell, and then they trigger it to go through apoptosis, or they'll actually spit enzymes on the surface and kill that cell. Right? And then, of course, you know where T cells mature. T helper cells, these are really cool. The T helper cells are interesting. Like I said, the commander-in-chief, here you have the T helper cell in the middle. It's talking to other T helper cells. It's talking to the B cells. It's talking to hematopoietic stem cells. It's talking to mast cells, T cells, natural killer cells. All of these cells are being told what to do by the T helper. Unfortunately, the HIV virus attacks T helper cells and kills them off. So when this is dead, these things don't like to talk to each other out here. So you can see that these T helper cells don't want to talk to these. These B cells don't want to talk to these other cells. So if you lose the commander-in-chief, you lose communication between all the branches. It becomes chaos. That's how HIV kills you. It gets so chaotic in there that other infections come in, swoop in, and kill the person. So T helper cells, they help because they're actually telling all of the neighbors what to look for. T helper cells come in two flavors. You have Th1s and Th2s. Th1s, they talk to T cells. They stimulate cell-mediated immunity. So they talk to the TC cells. They tell the TC cells, hey man, I saw a bad cell over there in the corner, go kill that for me. Okay. The Th2 cells are important for developing humoral immunity. So what type of cell do they talk to? They talk to a B cell. So they interact with the B cell and tell the B cells what to do. So here you have T cells. T cells differentiate into T helper 1s and T helpers 2. And they can get back and forth across membranes. If they slip into your brain, they're going to tell your microglia and other cells, kill brain cells, kill that myelin. It doesn't belong here. So those are the different branches of T cells that you need to be familiar with. Next, the NK or natural killer cells. These act a lot like T cells, so I saved them until the T cells to talk. But what's important about these is that they recognize self cells. They'll go cruising through your body, and they'll attach to this cell they got close to and say, hey, are you Shannon's cell? This cell says, yep. And the natural killer says, okay, keep up the good work. Let's move along. But if this comes along and detects, who are you? And this cell says, I'm Shannon's cell. and this other receptor has been mutated so it doesn't bind. Now this Shannon cell is saying, oh, I don't feel so good. I think I've mutated and there's something wrong with me. So the natural killer cell will turn on apoptotic or apoptotic effects, and it tells the cell to kill itself. So the cell lyses. But it lyses in a way that's apoptotic, not necrotic. Necrotic would spread all that virus everywhere. With apoptosis, it kind of implodes. It pulls everything to the center and dies there, holds everything together. Right? So when you see people that have deficiency in natural killer cells, you just see higher rates of virus infections. So higher cancers, higher herpes simplex comes out with people that have deficiencies in their natural killer cells. Right? So let's see if you can piece it together. Make sure you know where the MHCs, the APCs, the T and the Bs are all coming from. So here you can see the MHC is made in the rough endoplasmic reticulum. The antigen is put on it. The antigen is carried out here and popped up on the MH2 cells, antigen-presenting cells. Otherwise, these endogenous things are made to put up on the MHC1s in every cell in your body except red blood cells. Here you can see the T lymphocytes come cruising along. They look at this cell, they plug into it with their little CD8 receptor, and they say, hey, do we know you? The cell says, well, I did, but unfortunately I'm infected with a virus. So now suddenly this T cell says, well, then kill yourself. I get your back. I'll make sure that none of that virus gets away, but you go ahead and do apoptosis. Right? So kind of put them together. You can do the same thing here. So you can take an antigen-presenting cell like a macrophage with its MHC2 and antigen. It talks to a CD4 cell, a T helper cell, and that T helper cell talks to everybody else. They keep everything running smoothly. And then aging and the immune function, I already told you the thymus shrinks. So by the time you're in your 80s, it's about 15% of its maximum size. It's shrunken down. Unfortunately, a smaller thymus has been linked to having more autoimmune disorders. So having decreased efficiency at fighting off infections, but it causes problems. Autoimmune turns that up. Right? So decreasing B cells in the circulation is also decreasing T cells. The thymus isn't there to age them appropriately or develop them appropriately. So you see a lot of other symptoms like inflammation, so diabetes, cardiovascular, that become common. And then I put this little practice quiz at the end, so if you feel like taking it, you can, but you don't have to. So kind of walk through and ask yourself, do you really understand these different points? And that's it. See you in the next video.